Okay, so I'm going to just, so today in this lecture I'll just do some odds and ends that need to be, that we could finish. Essentially everything important that I wanted to say I have already said. So here is an example of which apply of a computation involving segregate classes. So let X be an n-dimensional variety and L be a line bundle on X. Let V be a linear system, that is to say that it is, V is a subspace of H0 of the global sections of L, and say a dimension of V equal to R plus 1. So then I suppose you would know that this choice defines a rational map into projective, from X into projective space. So how does one do that? So pick a basis, say S0 up to SR of V, and then define phi L. So this is a rational map. So I will write it with this kind of a dotted arrow into P of V dual, PR plus 1. Okay, so this is, but really this is actually in P dual, PV dual. So I don't necessarily have to do it taking this, but this way I can write a nice quick formula that this is phi L of X is equal to S0 of X colon S1 of X SR of X. And this, to get a point in projective space, you need at least one of the coordinates to be non-zero. So, this is undefined, this is not defined. In on intersection of ds. So S is in V. S not equal to C. Okay, so is equal to B. So here ds is equal to the zero scheme, set of zero scheme of S. So S is a section of L, so I can look at its zero scheme. So now this is a PR. Okay, so now I suppose you will have seen this that if you can resolve these indeterminacies of the map, right? So basically what you can do is blow up. So let X tilde be the blow up of X at B. Then there exists, so pi is from say X to X tilde to X. Then there exists a morphism phi L tilde from X tilde to basically projective space such that this thing commutes. So phi you have X tilde into X into P plus 1 phi L tilde. Okay, sorry, this is just a rational map, but this can be made to commute like this. Okay, so what we will do is, so one just comment about why this is possible. I mean, basically, whenever you have a map, a rational map into projective space, if it is defined on a smooth curve, right, then you can always complete it. So basically, that is because the place where it is not defined. If you look at the local ring, that's a DVR, right? But so that is something that you cannot do in this situation. Like for example, if you were to try to extend X sort of by continuity, right? So you approach a point where it is not defined by along various curves. But the problem is that if your curve is different, you get a different limit, right? So that's the kind of problem you run into. But if you blow this up, then then basically the scheme where you were having a problem becomes locally principal, and so it is sort of like you're back in the situation of a curve. Okay, and that's basically how you're able to do this. And so also now the thing is that for phi L tilde upper star of O1, so if this had been a morphism, then O1 would have been L, but the pullback of phi L upper star of O1 would have been L, right? But now here, what is the idea? The idea is that out of this L, you remove this part, right? You basically remove the exceptional divisor. So yeah, so let E equal to pi be pi inverse pi inverse of the exceptional divisor, right? So this is equal to pi upper star of L minus E. Okay, so this is something that you would see in most elementary texts. So now what I want to do is so definition. I want to compute this following quantity. So definition. So degree of phi tilde of x tilde. This is what I would like to compute. So this is equal to so I should define what this is. So I'm trying to define what this is. So this is the degree of phi L tilde of the fundamental class of x tilde. This is what it is, right? So this is the definition. And I would like to get an expression for this. Okay. X is no. What do I need x proper? Okay, let's take it to be proper. I mean, I could. Okay, yeah.
Is there 5 to the lower side? Is there 5 to the lower side?
Yeah. Yes, this is lower star. Yeah. So I don't know if we have probably not used this notation that if alpha is in a naught of x, then I define integral of alpha on x to be equal to the degree of alpha. So degree of phi L tilde of x tilde, this is equal to the integral of it is equal to the integral of where do I want to do this? Yeah, on x tilde of C1 of so yeah, basically what we are doing is we are looking at okay, let me write this out. So this is equal to f upper phi L upper star of O1 to the n of x tilde. Okay, so this is what we want to calculate. So the proposition I will prove is that, so with above notation, this degree so this is C1L, so the integral of on x of C1L to the n minus integral, yeah, I mean this would sort of, this is sort of like, I mean if this were a I mean, if L were O1, then this is sort of like a degree of x, and but then there is this term, error term, CL. So this is CL. So this is the total, the Chern total Chern class. No, what is it? What is this called? Chern class or Chern current? No, this is the total Chern class, right? Yeah, total Chern class. So, so B. So this is over B of. So this is capped S BX. So let's see. So the degree of x tilde phi L tilde. So this is the integral over x tilde of C1 of. So now what is? I just wrote down this thing over here. So this is what I want to use over there. So C1 of phi upper star L minus C1 of OE to the n x tilde. Okay, so now you just expand this using the binomial theorem. So this is summation I equal to 0. Well, I greater than or equal to 0. Let me just write it like this: minus 1 to the I n choose I of C1 of pi upper star L. Pi upper star L to the power n minus I, and yeah, C1 of OE the I of x tilde. Okay, so yeah, this is pi. So what I'm going to do is transfer this calculation down here, but for that, yeah, this is equal to the integral over x of summation I greater than or equal to 0 minus 1 to the power I and choose I of C1L. So I'm using the projection formula here, and so now I have to push forward this part. So pi push forward of C1 of OE to the I of x tilde. Now, yeah, let us look at this. So, yeah, so I will basically just start writing this as intersections of I'm E with this class. So this is equal to. Yeah, so there is when I take I equal to 0, what happens is I get C1 to the C1L to the power n. This will not be there, and I will just have x, right? So I will separate out that term. So integral over x of C1L to the n of x. So I'll write this term separately, and then I will write plus summation I greater than equal to okay, let me write greater than equal to 1 for now, and n choose I of C1 of L to the power n minus I, and what I get is minus 1 to the power I, and yeah, so now I will write this as just E, and okay, so pi times, so pi rho star of E to the power I minus okay, yeah, just I times x tilde. Okay, so now the thing is that basically I'm trying to get a Segre class type of expression out of this kind of thing. So this is equal to integral over x C1L n x, and so I will get minus, I will take out a minus sign from this and write this as n I greater than equal to 1 to n choose I C1 of L n minus I. Okay, times minus 1 to the power I minus 1, okay, so pi lower star of this, okay, no, maybe this is fine, minus 1 times pi lower star of, so what this will be is actually e to the power I minus 1. So the one of the e's, I use it to act on, I take the intersection of e with x tilde, I just get e. And then, so what I will get here is, okay, so I will write this as E. Okay, so now this is starting to look a little bit familiar, because see, this is, what is E? E is actually O minus 1, right? So, okay, so that is, so this is equal to integral over x of C1L of x minus summation I is equal to 1 to n choose 1 I of C1L to the power n minus I. And so using the fact that E is so I can use these minus signs, and I will write this as pi lower star of O1, so the Chern class of O1 to the I, acting on the projectivization of the cone of x of E at okay, no, what do I want to say? Yeah, of B at x, right? That is what this is. So now, yeah, actually I forgot to write an integral sign. Yeah, this is all, yeah, this is all in the integral actually. Okay, so maybe I will write this, did I not write integral signs anywhere? Yeah, so, okay, so let me write this again here. So the thing is that because basically I'm taking degree, I only need to worry about the degree 0 part in all this, right? So the thing is that in this calculation. Now, when I take C1L n minus I, what do I need to pick out of this entire sum? I don't need the whole thing. I only need to take the degree I part. Okay, so in fact, what I can do is see, this is just a sum. I mean, this is just a single term. What for Segre class, what I would need is really a sum over all j, not just on I, but for all j greater than or equal to 0. So I can replace this sum, this single term, by a sum, right? Because it doesn't matter, because I'm only taking degree. So only the degree 0 terms will get picked out. So this is equal to the integral x of C1 L to the n of x. Okay, so I think I have a small issue here. I seem to have, when I take the total churn class of a line bundle, it is 1 plus C1. So this is already good enough, right? This is 1 plus C1 to the n, except that I'm missing the leading term. I'm missing the 1. Well, I wrote it over here, but actually, okay, let me. So yeah, so what I'm saying is that here I can simply write the s of b comma x.
Shouldn't that go minus?
Huh?
In the last to last time, C1 of O minus 1 shouldn't that be? But you are doing it by e to the power I minus 1, right?
Yeah, e to the, oh yeah.
O of e is O of minus 1.
Yeah. Yeah, I thought this was getting absorbed.
I minus 1. I minus 1. I start off.
Here. This should be, yeah, this is I minus 1, that is true. Is that it?
Yeah.
Okay. Yeah, still, I mean, yeah, so the thing is that I'm replacing this now by this simply because I'm just doing degree.
Huh? O of O minus 1 that you do. Because O of E is O of minus 1.
Yeah, but I got this minus, that's why I used minus 1 to the power I minus 1. That was used over there. No, my problem here is only that, see, I've essentially gotten what I wanted, except that, see, this is, this thing, what, see, I can replace this x by b because this is all happening over b. Okay, that is not a problem. The thing is that I'm missing one term, which is probably because of a calculation error somewhere. The thing is that this is 1 plus, this is C of L to the power n minus 1, actually. No, not minus 1. This is, so I'm missing the term C1L to the n. That is the term that I'm missing. But is that really problematic? Let me think a minute.
I think one has to somehow get to an integral over b, right? So at some point.
No, that is not a problem. See.
Computation should be taking place. I mean, basically, that just means that the computation should be taking place in A0 b, right?
See, when I have this class is entirely supported over B, right? I mean, well, I mean it's yeah. Sorry, the push forward of this class is supported over B, so that is not the problem. No, so the only term I'm missing is C1L to the power n acting on the Segre class. So if I manage to get, so but is that 0? No, that can't be 0. What? Yeah, but there is L is a line bundle, so there is only 1 plus C1, right? So
if was dimension greater than equal to 2, then it would be 0. We don't know that.
Yeah, and I mean this is not that term. I don't know why it is missing. It should not be missing for degree reasons or anything. Okay, maybe.
So what do you, so that CL is supposed to be 1 plus C1, right? 1 plus C1 to be n.
Yeah. So CL is equal to 1 plus C1L.
So if you expand that term.
So that is the thing, no? So that's what I'm trying to get over here. This is,
So just the Segre class is remaining, right? The single term is
see, I've got the Segre class which I wanted, right? Out of this, I've actually, gotten the entire binomial expansion except for one term.
except the first term.
Yeah.
What is the integral of the Segre class over
So that's what I'm trying to think. So see, C1 to the n. So basically what you are doing is taking the degree of the Segre class, but the Segre class, where does that sit? There is no reason there is no reason why it should be 0 or something. I mean, I've gotten through much of this nonsense by introducing fake terms, right, which was 0.
Second class is power I. Even over power I.
This one.
It should be power I for second class.
No, but I mean, I see. No, that is not the issue. Because I'm summing over I greater than or equal to 1.
Okay.
So that is not the problem. Okay, so maybe I will just show you a place where this is applied, assuming the formula. What you can, so a related thing to this is that suppose you have, so X is a hypersurface in Pn. Well, let's say Pn plus 1. Okay. So it's an n-dimensional thing given by f equal to 0. So then what you can do is for at any point which is smooth, you can take the tangent hyperplane, okay, which is now sitting inside. So this is, let me say this is P of V. So the tangent hyperplane will sit in P of V dual, right? So we will define this map. So consider the rational map X from X to P of V dual, where X goes to tangent plane, tangent hyperplane. At X. Okay, so this is undefined. So where will this be undefined? Precisely where the hypersurface is not smooth, right? Where there is no tangent plane, which means that one of the partial derivatives of f has to be 0. So this is undefined. On the subscheme J, which is the 0 set of the of df of the collection df by dxi. Okay, so now so what is an example? Like if you take a so this is maybe I should say of degree strictly greater than 1. So if I take degree 1, then I just get the constant map, which is okay, which is not a problem. But for example, in the plane, if I take a conic, a non-singular conic, then the image is again going to be a conic. Okay, but if I take some higher degree curves, then interesting things start to happen. So for example, what could happen is that if there is a line which is tangential at 2 points, see the image of this, what can you say about the image of this? That will again be a hypersurface, right? So if I'm talking about curves, the image will again be a curve. But if there is a line which is, say, tangential to 2 points of the curve, then what will happen? What that means is that the image of this map will get a singularity, right? Do you see that? That suppose I have got a curve that is like this, and suppose there is a line like this. Now, as I take this, so this is the dual. What I'm getting here is a dual curve. So as I go over here, I mean, maybe I'm getting something like this, and then like this. So these 2 points will correspond to this kind of node. Okay, so this, now the thing is that if I try to get the dual of this again, then what will happen is that when I come to this point, suddenly I will get this entire line. In fact, see, at this point the dual will not be defined, right? But if you try to kind of do something, you will see you will feel like basically you have got to include this whole line, right? So that is the kind of thing that will happen. So that is, but if you don't do that, I mean, if you don't do stupid things and you understand that this is not defined, this map is not defined over here, and then you properly resolve the indeterminacies and construct the map, then there is a theorem which says that the double dual is the original variety. So fat. So this is by. So in characteristic 0, x. So yeah. So the image of this. Okay. So. Yeah, maybe I will should say first what x dual is. Let x tilde is equal to the blow up of x at j. So then what you have is x tilde x p of v dual. Okay, you have something like this. So this is. Okay, maybe I will call this map phi, and then there is some phi tilde like this. So I define x dual to be phi of x tilde, and then so there is this theorem that in characteristic 0, x dual is equal to x. Okay, so but what I want to do is just see what is the degree of the dual. Yeah, phi tilde. So yeah, so even though there seems to be some error somewhere in this, the result is correct. So we will just use it and see. So the degree of phi tilde star of x tilde. This is equal to the degree of the dual. So this is actually the definition. So this is equal to, yeah. So the thing is that, so if you look at this, yeah. Well, I think I erased the expression, but it's sort of here. So what is this going to be? So what is the degree of this map? Well, the rational map that you are constructing. So what is the degree of L? So D is see, the map that I'm constructing phi, right? It is basically given by degree d minus 1 polynomials, right? So what will happen is that this will give me d. This d is for this guy, and then times d minus 1 to the power n. Okay, and then minus summation. Okay, so I is supposed to go from 0, though I greater than or equal to 0, though we are not getting that here. So n choose I, and C1L is again d minus 1 to the power I, and so what we need here is just the not the entire Segre class. You just need the degree I part of it, right? So Si, so degree of Si, where Si equal to degree I part of Segre class of Jx. Okay. So yeah, I mean this is a sort of a, I mean understanding this dual construction is a bit of a classical topic, so you can find it in some books on curves and things like that. Yeah, so this didn't actually have much to do with anything we will need. This was just some calculation I was trying to show, except for whatever error I made here. I hope that maybe someone can fix it. So let me do a theorem which is perhaps much more relevant actually to what we want to do next. So we did all this deformation to the normal cone business. Which one here? Yeah, this is definition. Yeah, 1 second. What I mean by that is, actually maybe I should have said that I don't exactly want to look at the degree of the hypersurface. I want to look at this particular quantity, which is a little different. No, but it's actually the same here, right? Because no, it is birational actually. That's the point. It is birational. Phi is birational. Yeah, here it's not. It doesn't matter. So here actually they are the same. Yeah. Just sort of for dimensional reasons. Okay. Yeah. So as I mentioned, so the idea of doing this deformation to the normal cone business was that we really are interested in the situation where the normal cone is actually a vector bundle. And then, so to define the Giesian homomorphism, you only need to define it for the zero section of a vector bundle. Okay, so that and then one can use that to define it in more general situations. So I want to say something about that the Giesian homomorphism for the zero section of a vector bundle. So so let X be a scheme and pi from E to X be a vector bundle. Then let S from from X to E be the zero section. So we define S upper star to be equal to pi upper star inverse. So we know that. So based on what Amit did, that we know that pi upper star is an isomorphism. Okay, so that's why I can do this. Okay, so what I want to do is actually get a different expression for S upper star, which will be useful later. So here is a proposition. So with the above notation, if for beta in AK of E, let beta bar be an element of AK of, see, this vector bundle sits as an open subscheme of the projective completion of the vector bundle. Right? It sits in here. So what I'm saying is find some class which which restricts over here, which restricts to this, which you can always do, right? Because we know that the map from this to this is surjective, right? What is the kernel of the map? So the complement of E in this is the hyperplane at infinity, which is PE, right? So okay, anyway, so you can always find such a beta star, sorry, beta bar. So one way to do it would I guess that you just write down some beta as a sum of something. So if you have got some V in here, you could just take V closure, and that would be good enough. Anyway, so this you can find then S upper star of beta. This is equal to Q lower star. So I will explain the terminology, the notation of C. Let be a vector bundle of rank R. Okay, so now I'm taking CR of psi beta bar. So here Q is the projection from the E of E plus 1 to X is the projection, and psi is the universal quotient, universal rank R quotient, universal quotient bundle of rank R on E of E plus 1. So what this means is that this is the quotient of Q upper star of E plus 1 by the tautological bundle. Okay, so this is the formula that we want to prove. Okay, so let me just write some notation, and the proof is a bit of a tricky calculation, so I hope I get it right. So let F, so I will write F as F to be E plus 1, Q is equal to P of F, P is equal to P of E. So I have, okay, so you have Q, you have the inclusion of P in here, which is I, and so this is a closed immersion, and the complement is, so this is closed, this is open, this is E. Okay, and so you have got X over here, and you have this map. Did I write what this is? Yeah, this is pi. This is Q. This is J. I think I have enough symbols for now. Okay, so this is the picture. Okay, so what we want to do is we want to show that pi upper star of Q over star of CR psi capped with B bar, this is equal to J upper star of B bar. Because what is the definition of S upper star? That it is the inverse of this, right? And this is beta. So I just want to show this equality. Okay. So now beta. So as we have. Okay, I think I'm using a little more than just localization. We have, okay, let me write out what I mean. So we have a short exact sequence. AK of P okay, I was star and AK of Q, and then from here I have got J upper star of A K of E. Yeah, so Anand, can you help me here? So this, I want this kind of an exact sequence, short exact sequence. Okay, so this part, so this is closed, so on the left, but the exactness on the left will come from the projective bundle formula, right? So see, Q is basically P of, so this is equal to P of E plus 1.
Why is it satisfying? Why do you say this thing that?
So, okay, so because I want to prove, what do I want to prove? I want to prove this. No, so see, I take the inverse of the S, I apply pi upper star inverse to both sides, right? See, what is this? This is J upper star of beta. Beta is sitting over here, and no, beta, where is beta? Yeah, beta is sitting over here, beta bar is sitting over here. So J upper star of beta bar is supposed to be beta, right? That is the way we constructed these things. So that is just definition.
So by the projective bundle theorem, yes, there is that. Because
Yeah.
you know that, I mean, it's just projective bundle in rank 1.
Yeah.
Yeah. This is a sequence of 3 modules.
Yeah.
Right.
Yeah. Yeah, so this is, we have this by the projective bundle formula. So I think Amit had worked out the Chow groups of a projective bundle. So okay, so now using this, so what we see is that beta bar can be written as a sum of Q upper star of gamma plus I lower star of delta, where okay, so what am I saying? Gamma actually is okay, see, really what I should be saying is J upper star of some no, what I should be saying, so it should be coming from, so yeah, what I want to say is that it comes from, so there is, so using this sequence, so there is something that actually comes from this, right? So this is over here, and then I can subtract something like this, and then it is, no wait, what am I trying to say? See, basically what I want to say is that, yeah, okay, so what I'm saying is that where gamma is actually in A is coming from X.
For that, I don't think you need exactness for this. We have proved that Dyson kind of formula that there is a map, basically AKE to AKX that factors.
Yeah, I don't need it. Yeah, maybe, yeah. Yeah, I don't really need it to be injected, actually.
So what if you just apply J upper star to this?
J upper
So you want to calculate J upper star of beta.
no, so yeah, what I want to say is that I just want to say that this can be written as a sum where gamma is coming from X and delta is coming from P. Okay, so this is because the flat pullback to E is an isomorphism. Okay, so now here is what we will do. So we will show two equalities. So since beta can be written like this, and we want to do something over here to beta, we will show that Q lower star of CR psi of Q upper star gamma, this is equal to gamma. And second, we will show that CR of psi acting on I lower star delta, this is equal to 0. Okay, so the thing is that this is supposed to be enough. So let me just check that it is enough. So assuming this, pi upper star of Q lower star of CR psi cap beta bar. So this is equal to pi upper star of so let me write beta in this form. So Q lower star of CR psi Q upper star of gamma. So this will be one term plus pi upper star of Q lower star of CR psi plus capped with I lower star of delta. Okay, so now the thing is that by 2 this will become 0 and this will become gamma. So this should be equal to pi upper star of gamma, and this is enough because J upper star of beta bar, this is equal to J upper star of that. So Q upper star of gamma plus J upper star of I lower star of delta. And what is J upper star of Q? First you apply Q upper star and then you apply J upper star, that is pi upper star. Okay, so this is equal to pi upper star of gamma, and this is 0, right, because of this exact sequence. Okay, so plus 0. So then these two things will be equal and we will be done. Okay. So so let us prove these two equalities. So we know what CR psi. So what is this? So by the what we have is that, so this is the quotient of Q upper star E by O minus 1. So what you will get is this will be equal to the sum of Ci, C1 of O1 to the power I, Cr minus I of Q upper star of P. Right, I greater than equal to 0. Q upper star of CR psi capped with Q upper star of gamma, this is equal to Q upper star of sum of, so this expression, so I greater than equal to 0, C1 of O1 to the power I, and I have C R minus I of Q upper star E cap Q upper star of gamma. Okay, and we know how Chern classes behave with respect to flat pullbacks. So that is what we apply to Q over here. Okay, so this is equal to Q upper star. Wait, what did I do? Yes, there should be a lower star somewhere. What happened? Yeah, this was supposed to be lower star. This was also supposed to be lower star. This is lower star. Yeah. So summation I greater than equal to 0 of C1. Okay, so what I will do is I will write out these terms separate. So what I want to show is actually that this is equal to C1 O1 to the power R. Yeah, this sum actually only, okay, it only goes up to R actually, but it's okay. So this is like this, I equal to 0 to R plus, okay, so what should I write? Cap Q upper star of gamma and plus Q lower star of the sum of I is strictly less than R of C1 of O1 to the power I. So this is now actually Q acting on Q upper star of C R minus 1 E cap gamma. Okay. And so now the claim is that the second term actually vanishes. So claim is that Q lower star of sum I strictly less than R of C1 of 1 I of capped with Q upper star of C R minus 1 of E capped with gamma. Well, actually what I claim is that upper star alpha is equal to 0 for any alpha. Okay. So the reason is that so suppose alpha, so proof, take alpha is equal to say V. Okay. So then what you will have, what is going to be Q upper star of alpha? So it will actually be the class of the pre-image of V, which will be an R dimension, which will be the dimension of which will be dimension of V plus R, right? And now you are chopping it up with less than I times, right? And then this will be 0 when you push down. Okay, because you're simply not chopping it down enough. Okay, and so check dimensions basically. Okay, so what we see is that Q lower star of CR psi capped with Q upper star gamma, this is actually equal to this is equal to Q lower star of C1 of O1 R capped with Q upper star of gamma. Yeah, this is actually equal to gamma. So why is it equal to gamma? Yeah, this is actually equal to Segre class. Right? This is S0 of gamma, which is equal to gamma. Okay, we are in a vector bundle setting, so now we can talk about individual Segre classes. Okay, so that is one that takes care of one, and I think two is even simpler. For two, okay, so the thing is that I upper star psi has a nowhere vanishing section. Why does it have a nowhere vanishing section? No, what happened?
Direction 1 is there, so you take the constant section 1 of 1. So this is the nowhere vanishing section.
No, I am not understanding what you're saying.
So your direction 1 this section. So when that we have direction 1 also. So we have the constant 1 section. This is
over what?
Of the trivial number.
Yeah.
And this is the nowhere vanishing section.
Yeah. No, so is it as simple as that actually? Is it that? Yeah, is it? No, the way I was thinking was, yeah, maybe that is correct. So, yeah, E plus 1 has a non-vanishing section, nowhere vanishing section, and no. Oh yeah, that is true, because we are killing by some. We are taking the quotient over something else, right? So, yeah, we are not taking the quotient. Yeah, this is okay. Yeah. Okay, that is fine. But yeah, I thought, I mean, it would be, I think it should also follow from the fact that, I mean, I is basically, I mean, the inclusion of the divisor, the divisor that corresponds to, that is, the divisor PE, what is that actually? That is O1. Right, and I thought that gives. Okay, I had a certain argument along those lines, but I don't remember now. But anyway, so yeah, this. So using this, Yeah, so his argument is that E plus 1 has a non-vanishing section, right? Which will give you a section over here, because you are by O minus 1, yeah. That seems correct, right? Well, I mean, so a section of E plus 1 will give you a section of the quotient, but the question is, why is it non-vanishing? Okay, let me write down the rest of the argument, and then we can talk about why there is a non-vanishing section. So the point is that because there is a non-vanishing section, this I upper star of this is equal to 0. Okay, well, CR of I upper star, CR of I upper star psi, this is equal to 0. and CR of psi I upper star I lower star delta is equal to I lower star of CR I upper star psi capital delta which is equal to 0. So this takes care of 2. But yeah, so actually let me think, if I see if I can remember my argument actually. What was it? Yeah, I mean your argument I don't
Sorry, I gave a section.
You
could have a bundle which does not have a lower variation section and just take direct sum of 1.
yeah.
It would have lower variation.
But I mean, this is supposed to, is there an obvious way to see? Okay. Yeah. No, but so I'm taking the quotient of, so I have got a vector bundle E, I'm taking E plus 1, and then on that, I'm taking the quotient of that by the tautological bundle. Yeah. And so I want to see that the quotient has a non-vanishing section. Nowhere vanishing section. Nowhere vanishing. Because I want to conclude that the top chain class vanishes.
You can actually make to the point, right? So because it is a vector space statement that I gave this section, I have to show it is nowhere vanishing. So I gave this section, I have to show it is nowhere vanishing. So
yeah.
So that's a vector space statement. Over each fiber, I have to show it is nowhere. So then let's assume it is as a vector space statement. So then we can just do that. Draw the figure.
So Chetan, is O minus 1 in this case a subbundle of E or E direct sum 1?
No, E direct sum 1.
E direct sum 1.
Yeah. So yeah, the problem is that is the problem actually, that when I say O minus 1, that it's a tautological bundle of on the whole thing, right? P of E plus 1. So how are you going to say that it is keeping away that?
So an element of this P is a line in E. Now, on given any line, we have given an element of E direction 1, which is a constant in 1. Now, 1 does not lie in the line passing the line through it, and this is actually the fiber of minus 1.
So the only place where the tautological bundle will agree with the 1 actually is on PE, right? See the plus 1 part, right? No. So what I'm saying is see, what you're saying is that at any point, if you take the corresponding line in P upper star E, that is never equal to this 1 that you have added.
Yes, because the corresponding line is a line in E.
No, it's not. It is not. It could be in E plus 1. So, yes, because... No. PE plus 1. Oh, yes, you are right. Okay. I see. Yeah. I think that is... No, but yeah, so we are only looking in, you're taking the quotient of Q upper star E, right? So, oh, yeah. You are taking Q upper star of... this was, yeah, maybe I wrote something wrong here actually. No, this is, yeah, this should be E direct sum 1, yeah. Yeah, that was a mistake, yeah. No,
Is it Q direct, so Q is the map from the projective bundle to X, right?
Q is the map from P of E plus 1
E plus 1
to X.
Plus 1 to X.
Yeah. and I want the universal rank R quotient bundle on that. Okay, so that is basically Q upper star of, I had written something wrong here. It is actually Q upper star E plus 1 of Q upper star E plus 1 by O minus 1. Yeah, but that is okay. No. This see, this is fine. This is correct because I'm using the Whitney sum formula here. But see, that is okay because the Chern class of Q upper star E and Q upper star E plus 1 is the same.
Is this true at your base space is a point?
Huh? That's a good point.
Now E is only a vector space.
Yes.
So any vector space E is I take a vector space and I take on if I then O minus 1.
Yeah.
Take the quotient. There's a quotient and another.
I see.
It may be a two-dimensional vector space.
Yeah.
There is no one. This as written is not true.
I think you're also supposed to pull back that term E of E, right?
Pull back what?
When I upper star of I is claimed to have more.
Yeah. I'm only looking at the restriction on restriction on the hyperplane at infinity.
Yes. Not by one, right? By E. Right?
By E, yeah.
By E.
Yeah, but it's the one part that.
One part is 0 and from there is so that is the lower value.
Which section? Yeah.
Is that the same?
No, the last coordinate is 0, right? The infinity part.
On the infinity part, the last coordinate is 0.
But if the original section was lower vanishing, then on that part it would have to be lower vanishing because the last coordinate is 0. Right, so just restricted to hyperplane at infinity, it will be a lower vanishing.
Which section now?
The original section of E direct sum 1.
The non-vanishing section.
The lower vanishing section. So on the part that at infinity, that last coordinate is 0 corresponding to 1. So that the restriction of that section has to be lower vanishing.
So imagine the base space is a point. Base space is a point.
Base space is a point, then it is
one
yeah, so E is 1 and
the extra is 1.
extra is 1. Base space is point. Let's see that I can see that we have P1. Now what are you saying? P1 has an O minus 1 inside it. Quotient is O1. And it has no nowhere. That part at infinity is that single point.
No, that quotient has to be now.
And it has a lower vanishing section. So now it's a single point.
But then we have to look at that point only, right? P1
No, so
that quotient you are restricting to the infinity.
Yeah.
And there it has a lower vanishing section because
that thing is 1.
Yeah, so so then what is it then?
No,
over there?
The point is that the last, so So that novel vanishing section that you started with of plus 1. So the why is that it is 0 on the first coordinates corresponding to E, and then it is
Only on that extra 1 idea.
Yes.
extra 1, right?
Yeah.
But at infinity, that the coordinate is 0.
Yeah.
So it can't be vanishing on the
So that's basically what he was saying actually. Yeah. Yeah, okay, I mean, anyway, so that's basically it, yeah.
Okay, so let us thank Chetan for this